So my talk is going to be about advanced concepts for producing ultra-high efficiency of converting solar photons into both photovoltaic electricity and also solar fuels. I underline photovoltaics and solar fuels because both of these are very important goals of solar energy conversion. There's been, as we'll see, a lot of progress in producing photovoltaic cells and modules that are very efficient and low cost. And in fact, the cost of electricity from photovoltaics is now less than that produced from fossil fuels like coal. But there's still a lot of research, but no commercialization yet of approaches for converting solar photons into fuels. And I'll be discussing that field and the progress going on in that area. So, as I mentioned, the good news about renewable energy is that there's been a tremendous growth, an exponential growth, in fact, of the installed cumulative photovoltaic module capacity. So this is a plot versus time of the amount of gigawatts of photovoltaic panels installed. And the bars there show the data up to 2018, and the star is the next year, 2019. So you can see in 2019, there's a total of 634 gigawatts already installed, which is 0.6 terawatts. And last year, the installation of photovoltaics was the largest introduction of new resources for electricity than any other source, including oil and gas, and of course the major one being electricity and also nuclear. This plot is something that NREL produces every year. It shows as a function of time also the efficiency of the various systems. And I might mention that silicon has been the standard material used in photovoltaic technology for many decades. And that's shown over here. It's plateaued at about 25, 26%. But recently there's been a great increase in interest and progress in using perovskite solar cells. So that's this line here. And you can see in about 2013, it started out at about 16%, climbed rapidly, and now it's about equal to silicon. And this is a very attractive approach because it's produced at room temperature through simple chemistry, and the materials are surprisingly very efficient. And so in the future, this may be a replacement for silicon, because if you look at the long-term economics of this material, the production cost is much less than that of silicon, which requires refining silicon dioxide to silicon and then melting it and pulling crystals. That's the main process for producing most of today's solar panels, whereas the production of perovskite solar cells is much simpler and less expensive. So economics plays a big role here in the implementation and the utilization of solar energy. So what the goal is to reduce the cost per unit energy, which would be kilowatt hours of electricity. And a simple way this is done is to approximately multiply the dollars per peak watt by this factor 0.05 for just the module. And then it's, if you assume that the balance of systems, which includes the inverters and the hardware, everything else but the module, that's about equal in cost to the module. So if you multiply the dollars per peak watt by 0.1, you would get approximately the dollars per kilowatt hour. Now, in terms of the dollars per kilowatt hour, and here I plot the dollars per watt as a function of time, there's been also a very dramatic exponential decline in the cost of photovoltaics over the past, say, 40 years. So back in 1976, the cost of PV was about $100 per watt, which translated to about $7 or $8 US per kilowatt hour. And today the cost has decreased through a combination of research and economics of scale, such that it's in the range where it's lower than the cost of electricity from coal-fired power plants. And that means it's somewhere in a few cents per kilowatt hour. And that's a very dramatic increase. So, as I mentioned, in order to continue reducing the cost of, I'm talking now about photovoltaics, but the same applies to solar fuels, which is a much tougher challenge. And I might mention solar fuels is very important because two-thirds to three-fourths of the world's energy is consumed in the form of liquid and gaseous fuels, whereas electricity only accounts for about 25%. I mean, it's an important component, of course, of the energy picture, but it's about 3 times smaller than the amount of energy used as liquid and gaseous fuel, mainly for transportation and for industrial use in thermal applications in industry of various systems. So returning to the efficiency, which will be a main focus of this talk, how to increase the efficiency of converting solar photons into electricity and solar fuels. The Shockley-Queisser analysis, which was done about 1960 and is the first thermodynamic analysis of converting light into other forms of free energy like electricity and chemical bonds in fuels. One of the main losses is the fact that the optimum band gap for absorbing solar photons, and that's the minimum threshold energy to create an electron-hole pair from the absorption of a photon. That energy loss is due to the fact that the solar spectrum, which ranges from about 0.5 eV to 1.5 to 2 eV, covering the ultraviolet region, the infrared region, and the visible region. A large fraction, about 50% of the photons have an energy greater than the band gap, and that creates electrons and holes which have energies greater than the band gap. And their energy levels lie above the conduction band for electrons and for holes in the case of the valence band holes. And this process generally is very fast in terms of relaxing the high energy electrons and holes, and they're called hot carriers. And specifically, they'd be hot electrons or hot holes. That can occur in less than a picosecond generally in bulk materials. So that's why the efficiency calculated by Shockley-Queisser, which is 32% as the maximum thermodynamic efficiency, that thermodynamic analysis assumes that all of these hot electrons cool to the edges of their respective bands. So the electrons cools to the conduction band, the hole cools to the valence band, and that loses about 50% of the absorbed photon energy and converts the excess energy into heat. So how can one increase the efficiency above the Shockley-Queisser limit? And there's several ways to do this. And the most common way, which is in practice in use today in some commercial cells, it's very expensive, is to use multiple band gaps in series, each material having a different band gap, such that you reduce this heat loss because you more closely match the absorption characteristic with the solar spectrum. But the one that we'll be focusing on in this talk is the one in red, which is to use the excess energy of the hot electrons produced by the solar photons with energies greater than the band gap. Or also, I might mention that we'll briefly mention the fact that this can be achieved in molecules, and this is called singlet fission, when you can convert a single photon into two or more, well, generally two triplets, when the triplet state is halfway between the ground state of the molecule S0 and its first excited state S1, the triplet energy, if it's halfway between that excitation to, well, from S0 to S1, can produce two triplets from a single photon, and those triplets can be split to produce electrons at that energy, half of the singlet S0 to S1 transition. There are other approaches, and these are described in this book down here if you're interested in looking at other ways to beat the Shockley-Queisser limit. There's a couple of books by Martin Green called Third Generation PV, and two books by Antonio Luca and Antonio Marti called Next Generation PV. So I'm going to be talking about utilizing the hot carriers for useful work to beat the cooling and either extract the carriers or multiply the electron-hole pair, single one that's produced by single photon, into multiple electron-hole pairs by absorption of a single photon. So you can use the hot carriers two ways. You can extract them before they cool. So you create these high-energy electrons. They're hot, they have excess energy, and if you can extract them out of the device that absorbs the sunlight into the external contacts and use it to produce electricity, you can do that. If you can do that before they cool, then you will have a higher photovoltage above the voltage generally determined by the band gap when they cool to the band edges. Or secondly, there's a process called carrier multiplication, where you can use the excess energy if it's at least twice the band gap, or twice the, in the case of the molecules, the singlet to the S0 to S1 transition into two triplets. That multiplication in the process in molecules called singlet fission, but in bulk semiconductors, it's called the multiple exciton generation. And this is, in this review here, this process is explained. And what's important is that quantization effects in semiconductors enable the slowing of the cooling, of the hot carrier cooling. And this is a very important effect. And the introduction of quantum effects is created by making the semiconductors not bulk-like, but as small particles called nanocrystals. So that they're in the nano range between 5 to 100 nanometers, will produce, because of the confinement, quantum effects which will slow the cooling down. Now, the first process, as I mentioned, is to extract the high energy electrons or holes. I'll just talk about the electrons for simplicity before they cool. So in this diagram, this is the cooling process, which occurs in less than a picosecond. But if you can transport and transfer the electron across the semiconductor interface with a collecting phase over here, and it could be either a low work function contact to produce photovoltaic energy using hot electrons, or in the case of solar fuels, it would drive a reduction reaction of a molecular system here connected with the hole, which would be going the other way and doing oxidation on the other electrode. You could drive a reaction uphill in energy and thus create a fuel. So this shows the difference in the efficiency plot compared to the Shockley-Queisser limit. And the Shockley-Queisser limit has this characteristic where at room temperature, 300 K, the maximum efficiency was predicted in 1960 by Shockley-Queisser to be about 32%. But if you could extract all the hot carriers produced at one sun by say using a quantized system, you could double the theoretical efficiency to over 32% to about 66%. And that was first published in this paper in 1982. So what changed was the new physics that became apparent in the 1980s, which showed that when you go to very small particles in the nanoscale regime, small particles of semiconductors, you have many effects which are very important for solar energy conversion. One is you relax the requirement of conserving momentum, because momentum is not a good quantum number, because according to the Heisenberg uncertainty principle, there's an uncertainty if you multiply the velocity times the position. And since you know the position, because it's confined to a small region of space, you don't know the moment, you don't know the velocity, which means you don't know the momentum. So you don't have to conserve momentum as you do in the bulk. And that's very important because it allows the process of multiplication of the electron-hole pairs, which are called excitons in the nanoparticle, because they're confined and the electrons and holes interact and they associate with each other into an exciton. You enhance the Auger process. You slow down the cooling. You have a big increase in the theoretical efficiency because you can use the hot electrons either to produce multiple electron-hole pairs, or you can extract them before they cool to produce a higher voltage. The multiplication produces a higher photocurrent. Now the quantization is just shown here. This is the bulk material with a bulk band gap, but when you reduce the size below a size where the diameter of the particle is less than half of twice the Bohr radius of the material, which is a fundamental property of that material, the Bohr radius of the electrons and holes, then you get, instead of a discrete quasi distribution of energy states that form the conduction and valence bands, you have individual discrete levels in the conduction band and in the valence band. And sometimes you get a double set of levels, say, in the valence band because of the degeneracy of the band structure. So this just shows the density of states for different types of quantum regimes. You can have a thin film where you're only confining electrons and holes in one dimension. So that would be a film, and then you have a stepwise density of states. If you have a wire called a quantum wire, you would have density of states function like this, where you do have some densities of states in between the discrete states. And then in the limit where you confine the material in all three directions, you would have what's called a quantum dot or a nanocrystal. And then this looks like a molecule almost. You have very strong discrete states with no states in between the quantized levels. And this just shows a silicon nanocrystal. It's, this one's about 4 nanometers in diameter, and under TEM you can actually see the atoms of silicon here in a very nice TEM photograph of a silicon nanocrystal. Generally, the slowing of the cooling is accomplished most dramatically when you increase the concentration of the light. And in that case, you produce a hot distribution of phonons, and those phonons are, the population is so high that they can't dissipate their energy, and that's the final step in the cooling, to the lattice vibrations. So they live long enough to reheat the electrons in this process here and maintain a hot electron distribution over a lifetime, which can be much longer than the sub-picosecond scale when there's just one, say, one sun intensity excitation. And so this is being studied, these these slow cooling due to it's called a hot phonon bottleneck. You slow down the interaction of the optical phonons with the electrons, and that produces a bottleneck. Now, recently there's been very important advances and interesting advances in the utilization of perovskites. Perovskites are interesting because it's a material that was discovered by Professor Perovsky 100 years ago, but not really examined until the last 5 years in terms of applications to PV. But this material, and there's quite a large family of types of perovskites that are being studied now, but they have almost magical electronic properties and optical properties. So they're very good for PV. They're very good in being able to slow the hot electron cooling. So hot electron or hot carrier effects are being examined in these types of solar cells, as well as just conventional solar cells that currently have an efficiency equal to or even exceeding silicon. So these are some of the perovskites that have been studied and reported. There's been over 50 papers in the past 5 years on this topic. So it's a hybrid of organic and inorganic material. So for instance, the first one was methyl ammonium lead iodide. And you can have films or nanowires, and then you can introduce another organic component of the molecule in this methyl amide. And lead is an issue because it's toxic. So there's been a lot of studies to substitute tin for lead, and that works. And even substituting a new metal like cesium into a structure that can produce perovskite structure and slow the cooling and produce interesting solar cells. Now, the method of creating multiple electrons from a single photon is well known. It's known in bulk, but it requires a very high energy electron photon in order to do this, but it's called impact ionization. When you have a photon that's twice as big as the band gap, this extra energy, which if it's equal to another degree of band gap energy, can produce a second electron-hole pair, and that's how you get 2 electrons per photon in this process called impact ionization. But when it's produced in semiconductors, first of all, you don't have to satisfy momentum as you do in the bulk. So in the bulk material, you don't have the quantization, of course, and you've got a continuum, and you can describe it by this band structure, and the transition of the hole to the top of the bottom of the conduction band to excite a second electron-hole pair requires that the momentum is canceled. And I didn't show the second transition here, but there's a second process where this energy of the hole going from here to here just excites another electron across the band gap. The ultimate efficiency is a little bit lower than the Shockley limit or the hot electron extraction, because in the hot electron extraction, you use all the hot electrons, and even the cold ones get heated by the hot ones up here. And there's some intermediate temperature describing these hot electrons, and you extract them all at a higher voltage and get that higher voltage. But in impact ionization, or MEG, multiple exciton generation, as it's called in nanocrystals, you have to get to twice the band gap before you get the multiplication. So photons between 1 and 2 times the band gap will only create thermalized electrons, and you need to be twice the band gap in order to bring the onset of this process to get 2 electrons per photon, and that reduces the efficiency maximum from 66 to about 45. So in quantization, that occurs in semiconductors. It can be described here. You've got these discrete levels. You excite an electron that creates another electron by this relaxation process. But instead of producing heat, you give that extra energy to the hole that's in the valence band excited across there. And it turns out, because the cooling is slowed down because of these energy levels, you've got more than one energy of an electron-photon interaction, which is the process by which it cools. Then you can slow it down and allow this beneficial process of creating multiple electrons per photon, called MEG, multiple exciton generation, because the exciton is created from having the electron and hole confined in this nanoparticle. And there's different characteristics, but you want, in the ideal case, to have a staircase function, so that every time a photon is n times the band gap, you'll have a quantum yield of n. So if you're, say, 3 times the band gap, you'll get 3 electrons per photon in a single steep step like that, and so forth. For n times the band gap, you'll get a quantum yield of n. And you can see that the staircase will give you a maximum efficiency of about close to 45% versus the Shockley-Queisser limit, which is 32%. But if it's not perfect, if it doesn't give the staircase, but it, say, has an onset at twice the gap, but then has a linear function, which is a linear increase of the quantum yield with increasing photon energy, that's labeled as linear 2. So it's twice the gap. So L2, L2.5 means the onset of the multiplication is this number time this number of band gaps that you have in the photon energy. Now in singlet fission, as I mentioned, if you have a ground state and a triplet state, but you have a excited singlet state. So S0 and S1, this is the first excited singlet state. If the triplet state is halfway between, the transition from the S0 to singlet state is forbidden because it's a change in the principal quantum number. You can go this route by exciting to the singlet and then have this, if you slow down the relaxation or the radiative recombination or any other loss of this electron in the S1 state, you can produce 2 triplets from the singlet. And there's a nice review in the Journal of American Chemical Society in 2010 by Joseph Mickel. That's this one here in 2011. You can read more about singlet fission. So in terms of quantum dot solar cells, there's several ways to utilize the quantum dots in the solar cell. One is to just have an array of quantum dots and produce put them onto a supporting material like titanium dioxide, wide bandgap semiconductor, and then you create the multiple electrons per photon and transfer them into the supporting TiO2 substrate, and then collect the electrons on one electrode, and the holes will be collected on the second electrode. Or you can have them in a solar cell and just get the separation of electron and hole pairs in the device consisting of an array of quantum dots between two metal electrodes. And that would be this, like this case. And that case was shown to actually produce a quantum yield in the photocurrent greater than 100%. So that's the first solar cell ever measured that produced a current, a photocurrent that had a quantum yield greater than 100%. Because of the extra electron produces by impact ionization, or MEG in the case of the nanocrystals. And so that was published in 2011 in this paper in Science. Now, an important effect is very surprising that it's so dramatic, is that if you combine solar concentration with multiple exciton generation, you can, and then apply the theoretical Shockley-Queisser analysis, you can get the same plot as Shockley-Queisser, which is shown down here with an intensity of 1. So each curve has a higher intensity from 1 sun to the maximum concentration you can develop, which is 46,300 suns. And that would be if you had the solar cell on the surface of the sun, which, or in the interior, which you can't, but theoretically you just see how high it can go. But for achievable concentrations, which could be as high as 1,000, there are collectors for concentrating sunlight, either in PV applications or in thermal applications, to get concentrations of 1,000. You can see that, say we concentrated 500 suns, then the peak would be about 70% versus 32% for the Shockley-Queisser limit, and 66% for just solar cells, which are at a lower solar concentration. But you notice that the peak, unlike the peak that occurs in the Shockley-Queisser limit, which is between about 1 to 1.2 volts, electron volts is the maximum peak, which is why silicon is used so commonly in solar cells. It's right at the Shockley-Queisser peak. The peak for combining concentrated sunlight with the multiple excitons moves the peak into the far infrared. So you know, in some cases it's about 0.1 EV, but even at 0.2 EV, you get a significant high efficiency. And so if you fix the band gap, say, according to these different lines, so if you fix it at 0.7 EV, which is attainable in many materials today, and you concentrate to 500, the maximum efficiency is about 60%. And then if you have less desirable characteristics for the MEG, like the L2, where you have an onset of twice the gap, but it's linear instead of staircase, you'd be on this green line, and at 500 suns, you get an efficiency of about 46%. So there are some, it's interesting that silicon has a phase which does have a band gap of 0.3 EV, even down as low as 0.1. The bulk, as I say, is about 1.1, but there are very low band gap phases of silicon, like silicon 12, which is a gap of 0.3, so puts it into the region where if you can make it, it's a high temperature and high pressure phase, which is metastable at atmospheric pressure, like a diamond is related to graphite. And so you can produce it, and that it has some very interesting properties. Another material that has potential for application are the layered compounds, and they can have band gaps down here, even semi-metals with zero gap, but zirconium ditelluride, titanium ditelluride have band gaps below 1 eV, and so they're all good candidates for this combination of MEG and solar concentration. Now, just moving quickly, getting to the end, for solar fuels, it turns out the analysis shows you need 2 semiconductors connected either in the photochemical diode, like in this array, which is just two electrodes with 2 different band gaps. And if they're simultaneously splitting water, because the total voltage is greater than 1.23 plus the overpotential, which is about 0.6, you can't split water without having an external current, a wire, and it can just have a monolithic structure with 2 band gaps combined in this fashion. And you can see if you have that, you get a much higher efficiency as a function of the overvoltage, and that's determined how good the catalysis is at the surface where you actually do the electrochemical conversion essentially in the dark. And it's similar to what nature does in having 2 photosystems, but in the case of the semiconductors, it's called artificial photosynthesis. It does the same thing, absorbs 2 photons, combines 1 electron and 1 hole from each of the 2 phases, but uses the high energy electron and the high energy hole, 1 each from each half of the cell to give you the high voltage needed to split water, which ranges from a thermodynamic minimum of 1.23 volts to a realistic value of about 1.7 when you add about 0.5 volt of overvoltage, which reflects the inefficiency of the conversion. So I'm running out of time here, so I'll just end with a new effect, which is when you do fuel production water splitting with 2 layers. If you thin the layer, instead of having them both absorbing the full number of photons that are greater than the band gap of each layer, but allow some of the light that would normally be absorbed in the top layer to leak through. When you compare the case where you don't have thinning, but it's the case where you thin to the optimum thickness to allow some light to operate in both halves, you have an interesting effect where you extend the range of band gaps to give you the high efficiency. So this is summarized here. If you had 1x with a perfect water splitting cell where there's no overvoltage, which is unrealistic, but just for purposes of comparing a real case later on, if you didn't thin it, as soon as you start increasing the band gap of the bottom cell, keeping the top cell fixed, you would drop off rapidly. But if you thinned it so that you get this effect of allowing some light to pass into the bottom cell and have action in both halves of the cell, if you're at 100x even, you would have a maximum of about 55, almost 50, or 50, no, that's 50, yeah, 55, this would be 60. So 55% efficiency, say with 100x versus 45% when you're only 1x. So this is very interesting. And I'll just conclude here by just summarizing that the PV cost has plunged enormously in the past 42 years. It's half that of coal plants. You can use these to produce, if you have cheap electrons, you can produce lower cost solar fuels by conventional electrochemistry, but still doing the direct process, which is like artificial photosynthesis, not using wires, but that's still an attractive approach undergoing a lot of research. But I would emphasize there's no commercialization, there's no industry making solar fuels like hydrogen or reducing carbon dioxide to different fuels, alcohol fuels and whatnot today. But it's important to do it because, as I say, it's 3/4 of the energy consumed is in the form of liquid and gaseous fuels. Recently, there's been a lot of work in perovskites, and this is continuing. There's, like I said, 55 papers just on hot electrons with several hundreds of papers on other aspects of perovskites. Buried junctions where you have no wires, but you make a PN junction and coat it with the metal that is catalytic for fuel production is another approach that's being used. And when you couple MEG or singlet fission, the molecular analog of MEG, with solar concentration, you can get very, very high efficiencies, theoretically as high as 75% versus the Shockley limit of 32%. So I'll end by thanking all the people who contributed to this kind of work over the decades I've been doing it. And if you have questions, you can send me the questions at this address. Thank you very much.